Okay, so I'm still Jan-Pieter, so this is a presentation of PQC. So this is a work on dependencies and how these dependencies impact the failure probability of schemes. So in the NIST post-quantum standardization process, there's a lot of schemes that are based on the LWR problem or variants of this problem. And now, within a lot of these schemes have actually a small probability of failures. And this probability of failures might be quite bad because, and this is a result from another paper that you may have heard of. As you can see, for various schemes of this competition, you can actually, if the failure probability is too high, you can mount an attack that reduces the security of these schemes. And so, if your failure probability is too high, this attack might be quite devastating for your security. So, this results in a parameters trade-off, where it's possible to have smaller parameters, but this comes with the risk of a higher failure probability. And as we've seen, if this failure probability is too high, should be, attacks are possible on this scheme. And so it's of paramount importance to have good failure estimates, to have good estimates of the security of your scheme. Now, some schemes use error correcting codes. So internally in these schemes, they're going to use these error correcting codes to reduce the failure probability by correcting errors in the message that you are transmitting. And the advantage of this is that you can get smaller parameters of your whole scheme because you're reducing this failure probability. The disadvantages, well, there's more than one. The first one is that you have an increased code complexity. Okay. The second one is that it's actually becomes a target for side channel attacks. So you can mount side channel attacks targeting especially this error correcting codes and breaking the whole scheme. The third thing is that it's hard to get the failure estimate right. So for the experiments in our paper, we're always going to use LWR, which is one of the submissions to the NIST competition. It's based on ring LWE, and it makes very heavy use of error correction. So it corrects up to 55 errors. Now this plot is the failure probability of luck if we vary this error correction. So the real LWR would be somewhere here. It corrects up to 55 errors, but here we plot from 0 to 30 errors that we can correct. And this is according to their model, or actually the model that everybody nowadays is using to calculate the failure probabilities. Now we ran some experiments, and what we saw was that actually there is a discrepancy between what we saw in the experiments, running their code, and what we calculated using their model of this error probability. There's some discrepancy. The failure probability is actually higher, so this might be bad for security. And also, imagine that the real lag is 55, I mean, can correct up to 55 errors, so this discrepancy could become quite high. Okay, so that's what we're going to talk about today is how bad is this dependency, and how can we model this dependency. Let's first go into details about the ring LWE problem, because this is the hard problem that luck is built on. So imagine that in this paper we're working in these rings. So imagine that we have a polynomial with uniformly random coefficients between 0 and q. And we have two polynomials S and E with small coefficients. Now if we generate a ring LWE sample, which is alpha, and then a beta that we calculate as alpha times S plus E, then it seems hard to recover S and E from this ring LWE sample, and it's even hard to distinguish this sample from a uniformly random sample. How do we build a ring LWE based encryption scheme out of this? Well, first, Alice generates one of these ring LWE samples and sends this over to Bob. And Bob does exactly the same thing. He uses alpha, this public random matrix alpha, to generate his own LWE, ring LWE sample. And on top of that, he also uses B to generate a second LWE, ring LWE sample. And he sends both of them over. What he does on top of that is add the message to this V. He sends both of them over, and Alice does the same calculation as Bob. Bob takes B times S prime, so Alice does B prime times S. We subtract these two of each other, and we end up with this term for L. And if you calculate this, you end up with this whole equation where you have the message here, and then some noise. And luckily, these two noise terms cancel each other out. So both the noise terms that deal with these uniformly random errors, they get cancelled out. And what we're left with is a multiplication of small terms. So this is m prime is approximately m plus this term. So we have a decryption failure if any of the coefficients of this polynomial in absolute value is bigger than q divided by 4. Now, remember that we can use these error correcting codes, ECCs, to reduce this failure probability. So what do? Oh, we do exactly the same. This is exactly the same as the previous slide. The only thing we do here is that we encode the message into some error correcting code, and on the other side we decode it again. And this way we can tolerate up to t errors. So let's get some definitions straight. We'll say that if we have an error at the position E, if the absolute value of the ETH coefficient of this polynomial is bigger than q divided by 4. So just if an error happens at that location. So we will denote an error with AE and a success with SE. So a success is if there's no error at that location. And remember that we only have a failure if the number of errors is bigger than t. Now, just as in previous presentation, we will group these secrets and these ciphertext terms into S, which is all the terms of Alice, C, which is this 1' terms of Bob, and then E'. And we get this, which is exactly the same equation as here, but just some less writing. Okay. So now, how do we calculate this failure probability? Or how, in the past, did everybody calculate this failure probability? Well, the first thing we do is, we can actually, for this term, for the ETH position of this polynomial, we can fully calculate this probability density function. So we can just mount an exhaustive calculation, and we get this PDF. Notice that this distribution is the same at different locations of I. So whether we do it at the first or the second or the third coefficient, all these distributions will be the same. And it's approximately normal distributed, just to get you some feeling with what we did. How do we calculate then the failure probability from this error probability? Well, we assume that these errors are independent, and without an error correcting code, well, you can say that you only have a success when all of the coefficients succeed. So you have a failure if, and then you do success is 1 minus the failure probability. So that's why this is minus. So you have a failure if, with a probability 1 minus, and then 1 minus that probability that there is an error at the ETH location to the end, where n is the number of coefficients that you're working with. It's nearly the same with ECCs, but then, well, you need to account for the fact that you can have two, so it's a bit more complicated, but it's in the same spirit. Only problem is, well, as we've seen, this is not correct. There is some discrepancy. The question now is, where does this discrepancy stem from? Well, the error probability we calculated exhaustively, so I mean, there's no reason to believe that there is an error in this. We just calculated as we would. But notice here there's this assumption, the assumption that these errors are independent. And as we will show, this is not true. Why is this not true? Well, just to get you an insight, so a high norm of C and a high norm of S, well, the higher these norms are, the higher the failure probability is. And why is that? Well, we multiply S with C, and if this is bigger than a certain number, then we have a failure. So if these norms are higher, well, then we have a higher probability of failure. So, now imagine that we have a failure at an error at a certain location. That also means that we can imagine that this S and this C are also higher than we would expect, because we have a failure, so transversely also we would suspect these S and C terms to have higher norm. But if these norms are higher, this also means that the other coefficients have a higher probability of failure. So just with a Stoll experiment we can see that the errors are correlated, or that if one error occurs, it's more probable that another error will also occur. Okay? And this is actually bad if you have an error correcting code, because if errors are more flocking towards each other, they're more likely to go over this boundary of key errors. So, how can we model this dependency? Well, we already established that S, the norm of S and the norm of C, carry some causes dependency. There's also this other term, G. Well, there is no dependency from G. And why is that? All of the coefficients of G are chosen independently. And all of these coefficients only correspond with one of the error locations. So they're actually independent from the other locations. So there is no dependency through this G. Okay? And so now comes the main assumption from this paper is, we assume that these errors, the probability of errors at different locations, that they are independent, conditioned on the norm of S and the norm of C. So if we take out this dependency based on this norm of S and this norm of C, then we assume that the errors are no longer dependent. And now we can redo this probability estimation in 2 steps. So the first step is we again calculate the failure probability given the norm of S and the norm of C. So we fix the norm of S and the norm of C, and we calculate the probability of a failure. And we can use now, as before, these formulas of independence. Okay. And we actually do this calculation for every combination of S and C that we have. And once we have done this whole calculation, we take a weighted average over all of the S and C's. So we take an average and we take into account, of course, if there's a low probability of this happening, then we will get less weight into that example. So it's a two-stage process. Now let's go at the results of this calculation. What you see in the blue line is, again, this independency model as people were using before. The red line are the experiments, and the green line is the model that we propose using our assumption. And you see that the model that we propose actually fits nicely with the experimental data that we had gathered before. So then let's calculate this true for luck. So in their model, in their submission, they suspected for 2 of the versions of luck their failure probability to be, for example, to the minus 114. And in our model, we estimate that the real failure probability is actually higher. So he's, for example, here to the minus 92. And thus there is quite a big overestimation factor for these schemes. So you should really take into account these dependencies. Now over to schemes without error correction. What is, because there's still dependency, so do we have to take it into account? Well, we'll do the same reasoning. But now, I mean, it's analog, but it's the other way around. If we have a success at a certain location, then we would expect these norms to be lower than we would expect initially. So, it also means that at other coefficients, the probability of an error is also lower. Okay? So if we already have a success at one location, then the probability of success at all locations is actually higher. Which means that the failure probability is actually slightly lower than we would expect. So in this case, we're actually underestimating the security of our scheme. But it's only a small impact, as you can see. Maybe back here, as you can see here. Well, it's nearly the same. So there's only a small impact, but we're actually, for schemes without error correction codes, we're overestimating the security of these schemes. So, conclusion, it's really important to have good failure estimates of schemes, because otherwise your scheme becomes vulnerable to attacks exploiting these decryption failures. Now, schemes with error correcting codes are less efficient due to these dependencies. So these dependencies will make sure that your error correcting codes will be less good, and so you should take this into account in these calculations. And for other schemes without error correcting codes, they're slightly safer than expected, but you should not take this into account in the calculation because it's only a small impact. So, thank you for listening.